This video is about the definition of similarity. Let's get started. Before I give you the definition of similarity, I want to remind you about the definition of congruence, because there's a lot of things that are similar between the definition of congruence and the definition of similarity. Remember that two figures in the plane are congruent if there exists a finite composition of basic rigid motions or a sequence of rigid motions that maps a figure onto another, and being very precise about which rigid motions those are. Okay, that's a review about the definition of congruence. So let's now transition and talk about the definition of similarity. The definition of similarity is two figures in the plane are similar if there exists a dilation and or a sequence of basic rigid motions, meaning translations, reflections, and rotations, that maps one figure onto the other. So, some of the characteristics of similarity that I want to point out is that when you use dilations and rigid motions, one thing that happens is that angles will stay congruent. The next thing is that side lengths, with rigid motions, they stay the exact same length, but with dilations, we've learned that they're proportional. Okay, and so if you're using a dilation, then one characteristic of similarity is that your side lengths are proportional. And the last thing I want to point out is that if angles are congruent and side lengths are proportional, then it's the same shape but a different size. Okay, so those are some characteristics of similar figures. Now let's look at actually finding those dilations and or sequence of basic rigid motions that will map one figure onto the other. Okay, in question A, we are looking at, are these two triangles similar? If so, what are the similarity transformations that map one onto the other? Okay, we will write out and graph the sequence of similarity transformations, meaning dilations and rigid motions, and we'll be precise. Okay, if not, then why not? So the first thing that I look for is I look to see if they even look and seem to be proportional in size, okay? Because if they're not, then I'm going to stop and not worry about finding rigid motions and dilations that map one to the other, because they're not even similar to begin with, okay? And the way that I look at this, it's kind of hard to look at, slanted lengths if I don't have to. Like, that's a lot of work, and then radicals or decimals, and anyway, so it's a lot of work. So what I tend to prefer is to look at, like, from A to B, instead of looking at this length and this length, I prefer looking at kind of this horizontal component and this horizontal component and this vertical component and this vertical component. Okay, so if segment AB, the ratio between segment AB and LM, if that's the same ratio as AC to LN, then these horizontal and vertical components will also be proportional. So I'm going to look at, this is 3 and this is 2. Okay, and you can look at either 3, big over small or small over big, as long as you are consistent as you go throughout the entire figure. Okay, I'm going to choose big over small in this example. Okay, so I'm going to look at 3 over 2. Okay, and is that the same as, this is 6 and this is 4. Is that the same as big over small, 6 over 4? And yeah, it is. Okay, let's look at some others. Okay, I'll look at AC and LN. So I'll look at this horizontal component and this horizontal component and this vertical component and this vertical component. Now those are 3 and 2 and 3 and 2. I already have a 3 to 2 ratio up there, which also is equal to the other ones that are there. So I'll look at the last bit. So I'll look at BC and MN by looking at this vertical component and this vertical component, and this horizontal, and this horizontal, okay? Again, we have a 3:2 ratio, which I already have, and this is 6:4, which I already have as well, okay? So all of those kind of fit with this 3/2, 6/4. It's the same proportion all the way around, and so these, I'm very convinced, are proportional. Okay, so with that in mind, I'm now going to look for rigid motions and dilations that will map one onto the other. Now, you have two options. Option one is to use a translation to map corresponding points onto each other. Like I can map N onto C and then use point C as my center of dilation. Or I can map L onto A and then use point A as my center of dilation, okay? Or M onto B and then use point B as my center of dilation, okay? That's an option for us. I tend not to go that direction because it's an extra step, okay? The truth is there is a way that you can find the center of dilation, the perfect center of dilation without too much work. And so I tend to go that route, and for a problem like this, I will do one similarity transformation, and that is the dilation, okay? So the way that you find the center of dilation is you connect corresponding points with a line. So if you have a ruler, it's a lot easier with a ruler. I don't, so I think about slopes as I kind of draw this line to be as straight as possible. Okay, so those are all concurrent, and they will always be concurrent if the triangles are proportional. And this point of concurrency will be the center of dilation. In this case, it's 2, -3. Okay, so I have my center of dilation. I have a scale factor right here, this 3/2 that I kept seeing. As long as you're using corresponding ratios, then the ratio you get over and over and over again is the scale factor. So here is my single similarity transformation. I will again say where I start and be very precise about my similarity transformation. And there's one other idea to kind of give you before I give you the actual dilation. And that is that the scale factor is bigger than 1. So 3/2 is bigger than 1, and so it's going to get bigger. If my scale factor was between 0 and 1, it's going to get smaller. Okay, so because my scale factor is bigger than 1, I know that this will make it bigger, and so I have to start with my smaller triangle so that I can dilate with the scale factor of 3/2 and get bigger and arrive perfectly onto triangle ABC. Okay, if I wanted to go from big to small, like from triangle ABC to triangle LMN, then I'd have to use the scale factor of 2/3 or the reciprocal of the ratio that I had been finding. Okay, but I'm going to go from small to big and keep my scale factor as 3/2. Okay, so we're going to dilate triangle LMN with a scale factor of 3/2 centered at 2, -2, and this maps triangle LMN onto triangle ABC using similarity transformations. And so triangle LMN is similar to triangle ABC. This is a new symbol for us, and this is the symbol for similarity. Okay, it's just like congruence without the equals because it has the same shape but a different size. Let's try this next one. First, we're going to check the ratios. So I'm going to look at DE and ST because they're both vertical. Okay, and I can again go big over small or small over big. I'm going to go small over big, so it's different than last time. So I have 3 over 1, 2, 3, 4, 5, 6, 7, 8. 3 over 8 is that ratio. Okay, if I look at comparing DF and SR, I will look at these ratios and these ratios. Again, I prefer corresponding ratios so that when I'm done, I get my scale factor. Okay, so this is 5 and this is 2, and so is 3 over 5 the same as, I'm going to be small over big, the same as 2 over 5. Is that the same thing? And the answer is no. It's not the same thing. Okay? And if we look at the last one, this and this, I have a 1 and a 3, and that's not the same as 1/3. Okay? And then I have a 2 and a 5, the same thing as before. Okay? So we're noticing that we're getting different ratios. And if this fails for any of them, then it's not going to be proportional. And because they're not proportional, we cannot find similarity transformations that can map one onto the other. Okay, that's what it looks like if they're not similar. So that's why you check the ratios. Similarly, for letter D, again, if you look at this, I'm going to need to do a rotation first. And I can either rotate the small one over or the big one over. Okay, and in this case, I think I'm just going to rotate the small one. So I'm going to rotate triangle. Let's call it DEF. And I'm going to need to go this way, which is clockwise, 90 degrees clockwise around. And you can pick any point, like point E or the origin. I'm going to pick the origin. Okay, and it looks like this. And now that I have that in the correct orientation, it's now very easy for me to check the ratios of the sides and to find the dilation that I would need to map triangle D prime, E prime, F prime onto triangle PQO. Okay, and it looks like this. I'm using the ratio that's bigger than 1 because I need to go from a small triangle to a big triangle. So I'm doing big over small, the image over the pre-image in my ratios. Okay, so we would need to dilate triangle D prime, E prime, F prime with a scale factor of 2 from the center point -4, 0, and that'll map triangle D prime, E prime, F prime onto triangle PQO using only similarity transformations, a rotation and then a dilation, and that proves or shows or verifies that triangle DEF is similar to triangle PQO. This video was about the definition of similarity. Thank you for watching.